Hi everyone, so for this chapter we are going to look at light and whether it behaves as wave or particle. So for this chapter 10 we are going to look at the wave properties of particle. Okay, this is the overview for the whole chapter. For this video we are going to look at 10.1, which is about wave particle duality. Particularly we are going to study about the Bruy principle. And then for 10.2, it will cover electron diffraction, which is Davison-Germer experiment, and also electron microscope. Okay, let's look at 10.1, which is about the de Broglie wavelength. So we can find the energy of a photon by using the Planck's quantum theory, which will give us the equation for energy of a photon. E is equal to hc over lambda, and then at the same time we can also get an equation for photon, energy of a photon, from Einstein's special theory of relativity, in which E is equal to mc squared. So m is mass and c is the speed of light, so m times c will give us the momentum. So we can replace the momentum in the equation of energy to get E is equal to pc. So now we have the first equation and second equation. We can equate these two equations together and get hc over lambda is equal to pc, and then we can cancel out the c, which will give us p is equal to h over lambda, and p is the momentum, which is the particle aspect for this equation, and then the wavelength or lambda is the wave aspect. So from this equation, we can see that light has momentum, which means that it exhibits particle property, and at the same time, in some situations, we can also observe that light will behave like wave. So it has both particle and wave aspect, and this shows that light is dualistic in nature. In some situations, it can behave like a wave. In other situations, it can behave like a particle or photons. And this phenomenon is called as the wave-particle duality of light. So there are experimental evidence to support this theory. So initially, we might consider the fact that, okay, particles are supposed to behave just like particles. But then due to experiments such as the double slit experiment, we can prove that it can behave as wave as well. Light can behave as wave. So the experiments that support light behaving as wave is the Young's double slit experiment and also the diffraction experiment. And the experiments that show light behave as particle are the photoelectric effect and also the Compton effect. And then Louis de Broglie, which was the guy who discovered the de Broglie principle, also suggested that matter such as electron and proton might also have a dual nature in which it can behave as wave and also as a particle. So previously we have talked about light, or specifically photons. So we said that light can behave as particle and also wave. So now we are also proposing that electron and protons will also have a dual nature as well. Louis de Broglie also states that any particle of momentum p, it should have a wavelength lambda, which is given by the formula lambda is equal to h over p, in which p is the momentum and p is mv. So you can replace P is equal to mv in the equation to get h over mv, where lambda is the de Broglie wavelength, h is the Planck's constant, m is the mass of a particle, and v is the velocity of the particle. Okay, and this equation is also known as the de Bruy relation or principle. This wave properties of matter is called the de Broglie waves or matter wave. And the de Bruy relation, this equation was confirmed in 1927 when Davison and Germer succeeded in diffracting electron, and the experiment shows that electrons have wave properties. You will study more about this experiment in 10.2. Okay, now we are going to look at example 10.1. In a photoelectric effect experiment, a light source of wavelength 550 nanometer is incident on a sodium surface. Determine the momentum and energy of a photon used. So we are given the wavelength lambda and we are asked to find the momentum and also energy. So to find the momentum P, we can use the Bruy relation, in which lambda is equal to h over p, and then we want to find p, so we have the lambda, which is 550 nanometer times 10 to the power of negative 9, and then h is 6.63 times 10 to the power of negative 34 divided by p, which is what we want to find. And then using your calculator, you will get p is equal to 1.21 times 10 to the power of negative 27 kg meter per second. And then to find E, we have to use the equation for energy of a photon, which is given by E is equal to hc over lambda. Then substitute in all your values. C is the speed of light, which is 3 times 10 to the power of 8 meter per second divided by the wavelength. And then you will get the energy, which is equal to 3.62 times 10 to the power of negative 19 joule. For example 10.2, we are asked to calculate the Bruy wavelength, lambda, for a jogger of mass 77 kg, which runs at a speed of 4.1 meter per second. And then for B, we have to find for an electron of mass 9.11 times 10 to the power of negative 31 kg, which move at the speed of 3.25 times 10 to the power of 5. So to find the wavelength, we can use the Bruy relation, in which lambda is equal to h over p, p is mv, so we get the equation in this form. And for jogger, the Planck constant is 6.63 times 10 to the power of negative 34 divided by the mass of the jogger, which is 77 kg, and then times by the speed, which is 4.1, and we will get the wavelength 2.1 times 10 to the power of negative 36 meter. And then for B, we want to find the Bruy wavelength for the electron. So we just use the same formula, but we will substitute the mass and speed of the electron in the formula. So h is the Planck's constant, and then we divide it with 9.11 times 10 to the power of negative 31 times by the speed, which is 3.25 times 10 to the power of 5. And then we will get the Bruy wavelength for an electron, which is 2.24 times 10 to the power of negative 9 meter. Okay, for example 10.3, we have an electron and a proton which have the same speed. So V of electron is the same as V of proton, which is V. And then the question asks us which one has the longer Bruy wavelength. So to find the Bruy wavelength, we have to use the Bruy relation, which is lambda is equal to h over mv. And then from here we can see that actually the wavelength is inversely proportional to m. So what we have to do is compare the mass of electron and the mass of proton. So we have the values here, and if we compare them, we can see that the mass of proton is more than the mass of the electron. So electron is lighter. If electron is lighter and the mass is lower than the mass of proton, so electron has lower mass, which means that it has a longer Bruy wavelength compared to the proton, because lambda is inversely proportional to m. If m decreases, then the wavelength or lambda will increase. You can answer this question by writing the equation and then explaining it using these sentences. Okay, and then for question B, we have to find the ratio of lambda E over lambda P. So to find the ratio between these two, we have to use the formula of the Bruy relation, in which lambda is equal to h over mv. So lambda E is equal to h over mev, and lambda P is equal to h over mpv. And then from this equation, we can cancel out h and also v. which will leave us with mp over me, and then we have the mass of proton divided with the mass of electron, and we will get the ratio, which is 1833.